Hello, my name is KR, and today we'll be taking a look at the nature of quantum gates and reversibility. And as discussed earlier, I'm going to be assuming that you already know linear algebra and a bit of complex numbers. Now, let's begin. To begin today's topic, we'll be taking a look at one of the most very interesting equations that govern quantum mechanics, and it will help us understand the nature of quantum gates, which forms the very basis of a lot of quantum algorithms. Now, let's go to the slides right here. Here is Schrodinger's equation. It's a bit scary, I know it is, but if we do the mathematics, you'll this equation right here governs how wave function evolve. Essentially, it tells us how quantum matter uh, behaves over time. If you try to find the formalized solution of Schrodinger's equation, it will look something like this. The state of the qubit at a given time is equal to its initial solution times this gigantic constant right here. Well, not really constant, because one of the variables right here is actually a Hamiltonian operator. This itself is unitary and can represent some sort of quantum gate, such as your Pauli X gate, your Hadamard gate, or your CNOT gate. Well, in the most surface level understanding. Now, what does unitary mean? It means given any matrix U, there exists so uh, that such that it has the following properties. Itself is actually the conjugate transpose. So what does it mean? It's the combination of two words, conjugate, meaning to essentially flip the sign of the complex part here, or the imaginary part of a complex number. Transpose, if you remember linear algebra, it's actually just the flipping of the side of this matrix right here. So from 1010, it's going to be 1100. So this property states na these two are found with this matrix. And since it is itself a conjugate transpose, if you multiply it by itself, it results to the identity function right over here. What this entire math garble right here means, since I is itself equal to the identity function, that means that whatever operation that is applied to twice on itself, it means it goes back to its original identical state. Whatever action, when you do it twice, it returns to the same old initial output, meaning it is reversible. This in the time equation means that any action you do in the quantum world, as long as it's like mm, still in its quantum how can I say this? As long as no measurement is made, actions have time symmetry. When you try to um operate on a quantum bit, unless disturbed or measured, you can essentially reverse or retrace your steps. Any consequence that a quantum gate has a one-to-one mapping to the cause. Any quantum gate is reversible. Quantum gates are by itself reversible because of the property of being unitary in quantum mechanics. That's a surface level understanding. Now, to understand this property of quantum gates, let us first understand classical ones. In classical computing, some gates are reversible. Right here, familiar to our back home in computer science. If we have a buffer gate, well, that itself is already the identity function. So whatever you do, it will just result to the same old state. If you have the NOT gate, it will go back to the same state if you apply it twice. So from 0, it goes to 1, and from 1, if you apply the NOT gate again, it will go back to 0. However, for multi-input gates, there will be a problem. Classical gates such as the AND gate right here and the OR gate right here are many to 1. Look at this. This information right here is lost. You lose information because you cannot map those same outputs back to the original inputs. They are many inputs to 1. They lose information. Remember, in order to build quantum gates, they must be reversible. A reversible gate is a one-to-one mapping. So how do we avoid this loss of information? To get around this, we use a powerful operation called the exclusive OR operation. If you know anything with um, a variable swap in classical algorithms, what you can do to swap two variables is to essentially apply the SOR operation many times by itself. So for example, let's say we want to swap A and B right here, which has 6 and it has C in hexadecimal. If we try to apply the exclusive OR operation on itself, A and SOR B, and assign it to A, we will get this first intermediary value. And if we use this intermediary value again, so it's going to be A SOR C, it will result to the value B. And we can assign this to, no, this is the value A pala. So this value right here is assigned to B. And since it's assigned to B, if we do the operation again, A SOR B, so we got A SOR 6, it will result to the original value of B, which is C in hexadecimal. What we did right here is that we swap these two values from the old initial values to the new ones. SOR can be reversible. And since SOR is reversible, we can apply this to multi-input gates. So let's see right here. One configuration of SOR to make a reversible gate is the controlled NOT gate right here. By definition, it takes in a pairs of inputs A and B and outputs the pair of A and then the SOR of B and A right here. So in terms of a circuit diagram, it will look like something like this. You notice na the input right here is actually outputted also back. Why? It's because we want to preserve information. We want to be able to swap our A and B again to make it reversible, right? Our goal is to make this reversible. And so it is essential now we move any input and also output it. There we go. And here we can demonstrate the power of reversibility in the CNOT gate by applying it twice. So if you've taken the pair of values 1 and 0 and apply the CNOT, by this it will become 1 0, 2 1 1. And if you apply CNOT again on this pair of values, it's going to be 1 0. And that's neat. So what are some other examples? Let's take a look at the Toffoli gate, or the control not gate. This can be thought of as the reversible equivalent of the classical AND gate. So it takes in three inputs, A, B, C, and it spits out three outputs, A, B, and C. So the this should be the AND, or the conjunction of A and B right over here. Let's erase this. There we go. Actually, we can put that parenthesis back. There we go. So let's demonstrate reversibility for this one. So C naught to these three pairs of numbers would result to 1, 1, 1. Applying C naught again, we will get 1, 1, 0. Now, these two gates are reversible and therefore can be used in quantum computing. That is why you'll notice that this will be used a lot in quantum circuit designs. And you also need to notice that since we can reverse these values, let's say for example for this one for CC naught, what we did right here is called uncomputation. Uncomputation. We computed some value, but we were able to reverse it to its original state. We uncompute it. This is essential because a lot of quantum algorithms use uncomputation to clean up these unusable inputs of, for example, A and B. Since we output those right here, A and B, we cannot use them anymore unless it's involved something with C. If you want to clean them up, we need to do some sort of uncomputation right over here. So we place another CC naught here, and we essentially get our original values back. It's going to be A, B, and C. You'll notice that a lot of quantum circuits are mirrored so that we can use these quantum auxiliary bits again. And that's about it for this video.